Thank you very much, Thea. And I thank the program committee for inviting me to make this historic, more or less, presentation. So after I retired in 2001, I was the co-editor of a book entitled The History of Human Nutrition in the U.S. Department of Agriculture. And that history ran from the late 1890s until early into the 2000s. As part of that, I learned an awful lot about the history of food composition, and I've taken a good bit of this talk from that book. Next slide, please. In thinking about this talk, rather than to just give you a listing of the tables and listings of all of the food composition information that has been published, I thought I would give you some of the inside information, a lot of the inside information and situations that either hampered or that pushed food composition over the years. And I've broken that down into two primary areas and a minor area. And those two primary areas are scientific discovery. What were the scientific discoveries throughout the century plus that pushed or that hampered food composition information? And then the technological advances. There were a series of technological advances that really promoted and helped us in the food composition arena. And then, of course, there was public policy, government acts, and that sort of thing. And this influenced both the food composition information or the food composition knowledge side of things, as well as how the food composition information was used, which I've shown on the bottom of this slide, to include, and I've tried to include as many items as I could think about where food composition is used. Next slide, please. So here's the beginning of food composition in the United States, a formal food composition tabulation in the United States. It's a publication that was written by Dr. W. Atwater and Charles Woods. It was published as a U.S. Department of Agriculture circular or publication. The first printing was in 1896. And it consisted of data from about 2,500 samples of commonly consumed foods. These data were brought together from a number of different sources. A lot of the data came from Atwater's laboratory. He had set up an analytical lab to look at the foods for a number of reasons. In those days, the composition of foods consisted of proximate analysis. And that proximate analysis dated back to the mid-1800s from Germany, which was set up specifically to look at animal feeds. But it still consisted of the common proximate analysis: moisture, protein calculated from nitrogen content, fat content as determined by extraction with an organic solvent, the ash content, and then carbohydrates calculated by difference. There was also an energy value for many of the foods, and this energy value came from the bound calorimetry systems that Atwater had set up as part of his human calorimetry studies. And Atwater and Woods then updated these data in both 1899 and 1906. Next slide, please. So why did Atwater and Woods put together this data? Why were they analyzing these foods? Well, again, in the late 1890s, late 1800s, there were a number of food and nutrient intake studies that were done on common families, particularly laborers. This was a period when there was not very much known about what was in foods that people were eating. This was also a time in the economy when some families were spending up to 50% of their income on food. So there was a need for information about what people were eating and what the nutrients were in those foods in an attempt to reduce the cost of these foods. Some of the early studies were conducted in 1886 by the Massachusetts Bureau of Labor Statistics, again, just to gather that type of information. Atwater's group at Connecticut Experiment Station was doing a number of these kinds of studies. Also in 1894, the US Department of Agriculture was funded by Congress to study the food and nutrition of man. And at the same time, Atwater was put in charge of the experiment stations at the land-grant colleges. His specific mission was to try to bring together the agricultural products that were being produced on the farms into foods that were beneficial to man in an attempt, again, to reduce the costs of those foods. In the 1898 Yearbook of Agriculture, there were over 200 studies funded by the USDA that were noted, and I've just given you a small sampling of the types of studies that were conducted. And these were primarily food intake studies or food disappearance studies. Again, with small groups, mostly working groups, although there were some college students involved in these kinds of studies. But this gives you a flavor of what those types of studies were in the late 1890s. Next slide, please. On this slide, I've tried to show the historical funding of food intake, dietary intake studies, food intake studies historically. And on the left side of this, slide, excuse me, I show the USDA funding of these studies. Again, starting with the early studies in the 1880s and 1890s, there was a hiatus in the funding of studies by USDA for about 15 years. And I have not been able to figure out what happened there. In 1923, the Bureau of Home Economics was established, which carried all of the human nutrition research, food composition research, clear through into the 1960s. In 1941, the RDAs were established as a result of the very large percentage of malnutrition observed in the recruits for World War II military action. The first RDAs were published in 1943. This shows you, again, gives you an idea of the types of studies that were funded by USDA, clear down to National Food Consumption Surveys, CSFII, and you'll notice that I show that there was a diet component added to the nutrition examination, to the National Medical Examination Survey, which became Haynes in 1971. Of course, that was combined together with the USDA surveys in 2001. On the right-hand side of the slide, I've indicated an area that I call diet and epidemiology studies. In the 1940s, Ansel Keys at the University of Minnesota began to question and ask whether there was an environmental component in the congestive heart failure, and the other cardiovascular disease issues that were being observed in the population. In 1948, Congress provided the funds for the Framingham study. And this was as a result of the death of President Franklin Delano Roosevelt, presumably from a combination of heart disease and stroke. And again, Framingham was started in, shortly after the funding was provided, and is currently in the third generation of those original subjects. A little bit after 1948, Keyes obtained the funding for his 7-country study, where he began to look at the environment, including diet, on the effects of heart disease. If you go down and look at the LRC, that's the Lipid Research Clinic study and the Mr. Fit study that was funded by the National Heart and Lung Institute in the early 1970s, and I'll have more to say about that later. In the late 1970s, Dr. Hennekens was funded for the Physicians One study, which began to look at a combination of diet and aspirin both on cancer and on heart disease. Shortly after that, Dr. Willett was funded for the Nurses One study, and I think that was the first study, or one of the first studies, where food frequency questionnaires were employed, which put an additional burden on food composition information. So this gives you a feel for at least one of the areas where food composition information has been used forever in this country. Next slide, please. I'd like to talk a little bit about scientific discovery, and it's the discovery of the vitamins. In the center column, I show the estimated year that the vitamin was identified as an essential nutrient for life and livelihood. And on the right-hand column, I've showed the approximate year that was tabulated in a table of food composition information. The primary thing I want to point out about this slide is notice the large number of years difference between identification and tabulation. Remember though, this is the early 1900s. We did not have chromatography equipment. We did not have atomic absorption equipment. All we had were separatory fundas. Do you remember separatory fundas from organic chemistry? That was one of the primary tools that was used to isolate organic vitamins, organic compounds, and then try to crystallize it and precipitate them. But that was one of the primary mechanisms of separations in those days. The data on the food composition, on the composition of vitamins in foods was done primarily with biological assay. And the biological assay system was the RAP. And so there needed to be a pure compound to establish levels of intake and levels of reference for foods. These were enormously laborious studies that required a lot of animals, that required diets that were devoid of the particular vitamin or nutrient of interest. And the variability and the accuracy of these data that resulted was in question, but it was the only tool that was available for the analysis of the nutrient in the foods. Next slide, please. I show on this slide some of the more recent food composition tables. The table, the small table in the center called tables of food composition, was the first tabulation, complete tabulation of data subsequent Atwater and Woods publication in the early 1900s. And it was put together by a committee from the USDA and from the National Research Council. If subsequent to that, that was in 1945. The light blue table on the right is the first of the Agriculture Handbook number 8. It was published in 1950. It was the work of Bernice Watt, Dr. Bernice Watt, and her crew at the USDA. Bernice Watt started working with the USDA in about 1941 or 42 and worked for 30 plus years on food composition in the department. The red book in the center is the Agriculture Handbook number 8, 1963 version. It was reprinted again in the 1970s. And the food composition book on the right is one of the notebook types of books that was published starting in 1976. It was published, data were published by Food Group. There were a total of 22 of these books published from 1976 early into the 1990s. Next slide, please. On this slide, I tried to outline what the data were in the various books that I just showed you on the previous slide. And you notice that all of the books that are on that slide had approximate analysis. Of course, this is a routine now that's done with all foods as part of the analysis. Calcium, phosphorus, and iron the data for those nutrients began to show up in the 1945 publication and were carried through all of the Handbook 8 publications. Sodium, potassium, magnesium began to be published in data for them began to be published in 1963 and again in 89. And copper, zinc, and manganese were published in the 89 version. You'll notice that the vitamins, the A, C, thiamine, riboflavin, and niacin, appeared in the 45 book again and all the other books, but B6, B12, folacin, pantothenic acid didn't show up. The data for those nutrients didn't show up until into the 80s, late 70s and into the 80s. Fatty acids, again, the technology for fatty acid analysis was very, very difficult until gas chromatography came along. And so there was very little data until into the 70s and 80s on fatty acids. Same is true of cholesterol and phytosterols. Amino acids were originally analyzed by microbiological assay until the amino acid analyzers came around. So this gives you a feel for the limited, what we would consider today to be the limited amount of nutrient data that were available in these earlier publications. Next slide, please. I wanted to now switch topics and talk about technological advances that impacted food composition. One of the major advances in spectroscopy was Arnold Bachmann's invention of the ultraviolet spectrophotometer. It was actually his visible spectrophotometer on which he figured out how to add a lamp that provided energy in the near UV as well as the detector. This is very important because some of the vitamins and many of the biological compounds have ring structures, phenolic rings that absorb in the near UV, that is the electromagnetic spectrum range between 200 and 400 nanometers. And this particular invention has been carried through with many detectors, particularly for HPLC and other instrumentation. Probably one of the inventions that has changed our society was the invention of the transistor by Shockley, Bardeen, and Bertain, and all of the additional patents that have been awarded that have made the large-scale transistor and large-scale devices for computers. Very important invention. Erika Kramer, working in Austria, figured out how to separate compounds that were volatile and could be carried along in a gas stream after they had been absorbed onto a packing. This was in 1947. This was towards the end of World War II. She was working in Austria. Her work wasn't discovered until into the 70s. I must say that the design of the instrument that she showed in her original publication was very similar to the instrument that we were asked to assemble and work with in Advanced Biochem Lab at Madison, Wisconsin in 1962. Column chromatography was discovered by Svet. He was a Russian biologist, a Russian botanist in 1906. His work lay idle for many years, and in part because it was in Russian, in part there was a tremendous societal upheaval in that part of the world at that time. The next invention or the next publication that came from column chromatography was the amino acid analyzer that Spackman, Stein, and Moore published in 1958. Beckman and several of the other companies picked up on that very quickly and produced amino acid analyzers. It wasn't until the mid-1970s that Horvath, working at Yale, figured out how to, similarly to gas chromatography, how to develop and put together high performance liquid chromatography. And again, that took off very shortly after his discovery and his publications into many different instruments. Atomic absorption spectrometer to analyze minerals was discovered by Welch in Australia. He had trouble selling his so-called selling his instruments in Australia, and the PerkinElmer picked up his discovery in 1962 and produced a huge number of instruments after that. And the inductively coupled plasma spectrometer came about in the 60s and 70s, shortly after scientists figured out how to stabilize the torch. This gives you a feel, and again, I want to emphasize that the period of time when these instruments were coming online and we could begin to use them in the laboratory for not only for food analysis, but for other analysis was in the period of the 1960s and the 1970s and beyond. Next slide, please. I want to talk about a little bit about the computerization of food composition data. Computers, as I indicated, computers were available early on, but primarily in the 70s. Early on, the people working in food composition at USDA began to visualize what computerization of the data might look like in the early 70s. Remember now, these the food composition data at this time was put out in tables and pamphlets and books. But most importantly, there were file cabinets and file cabinets and file cabinets in the department and where these people worked, full of spreadsheets with handwritten numbers on them. And the question was, how are these data going to be put together into a computerized system? There was a committee that was put together of government, food industry, and technology people. The first thing that they developed was the idea of a nutrient data bank where all of the data could be put in and worked with. There was some question about whether this could be used as part of food labeling. That was soon shot down because of the proprietary products, food products that the industry was putting out. First mainframe computer came on board in '76. Shortly thereafter, Handbook 8, the 63 version was available with punch cards and magnetic tapes. The database for standard reference was developed in '80. There was some kind of online access to data via a dial-up bulletin board in the late '80s, early '90s, and finally the things came online later in the '90s so that people could access the data directly. And in 2019, the food data central system was put together, and Dr. Fukagawa will talk about that in her presentation. Next slide, please. I want to talk just a minute about this meeting, the history of this meeting. In 1976, people had access to food composition data via magnetic tapes, or if you have a big enough truck, via punch cards. But that was it. The data was on the data tape, and there were no programs provided to how to use the data to develop menus, how to calculate nutrient intakes from food intake data, etc. Two people, a pediatrician at Denver and a woman in Seattle, were very frustrated about this. They got together, they decided to call an invitational meeting of people with similar concerns. That meeting was held in Seattle. Two people from USDA were there, Dr. Robert Rezac, under whom the food composition work resided, and another USDA person. But a very important person also was invited, and that was Dr. Loretta Hoover from the University of Missouri at Columbia. She, as part of her coursework, had begun to really think about how to program the use of the data that came through in magnetic tapes. And she became a very important consultant to the USDA as part of computerizing the data. The second invitational data was held, the second invitational meeting was held in Utah, at Utah State University the next year. And from there, then the meetings were open to anybody and anyone who wanted to come. The next meeting was held in Arlington, Virginia, a suburb of Washington, D.C. And the meetings have taken off from them ever since. Unfortunately, these virtual meetings, I feel, lack the person-to-person contact and the person-to-person discussion that is offered by these meetings, and where a lot of problems are solved. And we're currently, as you know, at the 42nd meeting. Thank you very much. Next slide, please. I want to talk a little bit about diet and chronic disease. Before the 40s, and at that point, there was, as far as chronic disease was concerned, there was, people had a kind of a dreadful feeling, and that if you had a relative that died of a heart disease, there was probably nothing you could do other than accept the fact that you're going to die at about the same age as your relative. It was, as I indicated, it was Ansel Keys and some of the other leaders that began to look at the environment, and one of the components of the environment was diet that they looked at. It was Dr. Fredrickson and Dr. Levy at the NIH in the early 1970s who made a commitment to really begin to look at diet and heart disease. As I indicated, they funded the Lipid Research Clinic study and also the Mr. Fit studies. The Lipid Research Clinic study was a multi-center study that looked at diet and the distribution of the lipoproteins in the plasma. Mr. Fit study was again another huge multi-center study that looked at cholesterol levels and the association with cardiovascular disease. As part of these studies, they decided that they needed a center for food coding and for nutrient analysis. They funded the Nutrition Coordinating Center at the University of Minnesota to do the work for the LRC and the Mr. Fit study. Very important for food composition. They also put money into the US Department of Agriculture. And the reason they did that is that they wanted to make sure that the food composition data resided in a federal agency and could be and would be retained there. NIH was not the appropriate place for it because NIH worked primarily on grants and primarily on the grant process, and there was not a guarantee that the food composition, that organization like Food Composition would remain at NIH. So they pushed the US Department of Agriculture to embellish and work on the food composition to the extent that there was matching funds were provided for a new laboratory at Beltsville called the Nutrient Composition Lab, with the mission of adapting new technology for the analysis of nutrients and other health components in foods. And at that time, the primary focus of food composition were fatty acids, cholesterol, and minerals. In 1980, by then, diet and cancer began to take off, beta carotene being the magic bullet in some people's minds to reduce the risk of cancer, as well as antioxidants. Next slide, please. On this slide, I've tried to tabulate some of the activities that resulted from the marriage of the push by NIH. I call it a sharp shot in the arm. I call it a kick in the seat of the pants to move towards a whole area of nutritional epidemiology. And at the same time, we had available, again, this was in the early 70s, we had begun to have available to us scientific instrumentation that allowed us to make separate molecules that were similar in shape and size and molecular weight, and be able to do an analysis of foods. Let me just point out a couple of areas. Again, fatty acids was the primary goal of the first studies with the heart, lung, and blood studies, as well as minerals. When I came to the laboratory in 1982, our group began to work on carotenoids. And this gives you a feel for the studies that were conducted and the collaborators that were involved. Again, the collaboration between NIH and USDA food composition activity really enhanced collaboration with other government agencies as well as with the food industry. Next slide, please. One of the issues that appeared early on in the work with the collaboration with Heart, Lung, and Blood was the whole idea of data quality. One of the first studies that was conducted as part of the collaboration with Heart, Lung, and Blood was a study on retail meat cuts, both fatty acid and lipid analysis as well as mineral analysis. And as part of those early studies doing generating iron data from meats using atomic absorption, it was discovered that the values that were coming out from the new data were about 2/3 of the values that were in the Handbook 8. It was discovered that all of the values in Handbook 8 had been calculated from the protein content of meat. So there was then the push to provide some estimate of how good were the data. So there were 5 criteria that were established in terms of the critical evaluation of the data. And there was an attempt to provide a data quality indicator in the nutrient data bank for the data. Unfortunately, there was not enough information from a lot of the data to be able to put a data quality indicator on it. So in the mid-1990s, the decision was made to develop a large program to go back and analyze with modern technologies those foods, those basic foods, and generate good data. This was called the National Food and Nutrient Analysis Program. It started in 1997. It was a huge, huge collaboration with NIH NIH institutes, offices, and centers, and it was also the US FDA was involved. As part of that program, there were several issues that needed to be resolved before it was felt that good quality data could be generated from foods. And one of the issues was the key foods. There was a concept put together about key foods, those foods that provide 3/4, say, or a majority of the nutrients in the diets of Americans. And these data were generated with the key foods data were generated from dietary intake studies of USDA, both USDA and Haines. Another issue that we have been dealing with from the start of when I moved to the food composition lab was, how do you select a representative sample of foods from across the United States? Joanne Holden and I talked to, I don't know how many statisticians, and the answer we got was either thousands and thousands of samples that needed to be analyzed, or we got a blank stare. And we said, well, we don't have the gross national product of the country to be able to afford to analyze thousands and thousands and thousands of samples. So we've got to figure out something. Joanne Holden and Abby Ershaw and others, as part of the National Food and Nutrient Analysis Program, worked with statisticians at USDA and came up with a program where the country is divided into 4 equal populations. Major food chains are used as a major source of supply of foods, and then samples are picked up both in major and in minor cities. And this has been reported on many, many times in the literature. The other issue was analytical control, quality control. How do we make sure that the numbers that we get are correct? And so there was a special laboratory developed by Kent Stewart as part of the Delta and the DASH program at Virginia Tech. This laboratory was renowned in terms of accurately and efficiently homogenizing samples and allocating them out. They were also then experts in preparing quality control materials based upon data that was available from reference materials from National Institutes of Standards and Technology, as well as from other metrology groups around the world. And they prepare and send out samples to contract laboratories for analysis. Also, there was a program developed that laboratories were qualified for their analysis based on samples that quality control samples for which the numbers were known for the nutrients. That program has now generated data from about 2,500 foods, and it's replaced a lot of the data in the database with data from foods that are currently in the marketplace and also that are rapidly changing. Next slide, please. I'm sorry I'm running over time. Dietary supplements. New area of food composition. The Dietary Supplements and Health Education Act was passed in 1994. One of the main things that came out of that act was the definition of dietary supplements. As part of the diet intake studies from N. Haynes and from N. Haynes in 1999 to 2002, about a third of the population was taking multivitamins and multi-mineral supplements. The question is, what was the nutrient contribution of these supplements to the individual? In 2002, there was a workshop held subsequent to the combination of the USDA food intake studies and N. Haynes. And one of the recommendations that came from that meeting was to develop an analytically verified dietary supplement database. The first database was published and presented in 2009, and there's been an update now in 2017 where not only the multivitamin and multi-mineral supplements the estimates are published, but also the first botanical dietary supplement ingredient-based database has been put forward. Next slide, please. I'm sorry I ran over time. This gives you a brief summary. I will not spend the time to go through it, but I'm trying to give you a history of the adventure through the food composition over the last century plus. I must say, as part of working with food composition for 20 years in the 80s and the 90s, it was very exciting. Although at the time we didn't, and when we were in the trenches, we didn't think it was very exciting, but in retrospect, this was a very exciting time. And it was a huge expansion of food composition information as a result, as I indicated, of the technological advances, the shot in the arm that we got from NIH and have received from NIH since those early studies in the 70s. Thank you very much.
Thank you, Dr. Beecher, for your review of food composition knowledge over the last century or so. And thank you to the organizers for the opportunity to speak on behalf of the Beltsville Human Nutrition Research Center team about the USDA Food Data Central. What is it and why is it needed? Details about Food Data Central are also available in our recent publication in the American Journal for Clinical Nutrition, and the reference is shown here at the bottom of the slide. There had been ongoing discussion about modernizing the USDA food composition databases in the decade prior to the release of Food Data Central in 2019. Several of the factors necessitating change are shown on this next slide. They include rapid changes in the food supply that are escalating, the rapid evolution of technology and communication, a skyrocketing demand for transparency and easy accessibility to data, the need for understanding the complex interrelationships between dietary intake and health is now greater than ever. And more importantly, there's recognition that food systems are global and impact food security, the environment, and public health. Therefore, high-quality food composition information is extremely important. Our vision for Food Data Central is shown on this slide, with FDC being the first step in the development of an integrated food web, with the ultimate goal of connecting food production to health of people and the planet. So what is Food Data? We see it as a site for centralization of food composition data. We have a research focus, fostering linkages from food production to food products to the plate to health outcomes. Food Data Central addresses variability in food components, including nutrients, that are inherent to the food, that are impacted by environmental factors, or steps in processing and food preparation. There is also incorporation of the Global Branded Foods Product Database that was released in 2016 as a result of a public-private partnership. Shown graphically on this slide, Food Data Central consists of 5 data types shown in the oval, with input from other data systems and connections to federal agencies and external collaborators. It's important to know that each data type has its own system for food categories and food groups, has unique data sources and unique principles that guide what is included in that particular data set. So as you can imagine, consolidation of diverse data sets comes with big challenges. Some of the challenges to consolidation include addressing data diversity in the context of the different data types, i.e. label, analytical data, survey information, experimental data, and more importantly, the different platforms on which the different data sets reside. Variation in metadata associated with different data types are also a challenge, as is harmonization of concepts. And I'll use as a case study food categories. If you were to go through Food Data Central, you'll see that there are approximately 400 food categories within it, spread over 4 different category systems. Each food category system was developed with a different end goal, and external food category systems are not represented. So the overall biggest challenge, however, for Food Data Central is finding ways to enable users to get what information they want and to make most of the data that we have available for them. We plan to address some of these challenges with the different features offered in Food Data Central. Some of these features are listed on this slide and include food and component searches, data type documentations and field definitions, multiple download options, inventory and update logs, application program interface or API accessibility, links to related research data, and all of this development is guided by feedback from users and stakeholders such as yourselves. Two examples of features follow in my discussion. The first is that of the integrated search. If you were to enter Apple on the home page, and this is a screenshot of the result that you would find for the search of Apple, you'll see that the data is represented in 5 tabs at the top that represent each of the data types and includes the number of items found in that data type for the food that you have listed of interest. If you click on one of the tabs, you'll get then a listing of the items that are available in that specific data type for the food that you have done the search on. Our most recent release of FoodData Central was in April 2022, and it includes 184 foundation foods, approximately 8,000 SR legacy foods, approximately 7,000 survey foods, and approximately 382,000 branded foods, in addition to 26 experimental foods. Another feature that was released in April 2022 is the inventory and update log. It appears on the home page, and I have it blown up here so you can see it a little more clearly. And in this case, we are saying what is new, or presenting what is new in April 2022, and then what we have planned for October 2022. As a reminder, FDC is released twice a year, usually in April and October of the calendar year. So it's obvious that we've entered a new world of food composition data at USDA. We believe that FoodData Central has the responsibility to centralize data types and add new ones as needed, to develop multiple ways to interface with the data, to encourage input from and management of multiple data streams, and to be open and transparent. The user has a role that depends on having some basic technology skills, and most importantly, an understanding of each data type for their user-specific applications and interest. So now I'm going to move to the 2 new data types, foundation foods and experimental foods, that appear in FDC. Foundation foods will include single ingredient foods and basic food ingredients. The values for food components in foundation foods, including nutrients, are all analytical. The data are presented on individual food samples that are snapshots in time of that particular food. We hope that the insight into the variability of food in the marketplace will assist in your use of the information that we provide. We do provide averages for each of the components, but as you will see, the variation in the values contributing to the average, and will have to decide for yourselves the most appropriate numbers to use for your specific purposes and application. Our sampling approach for foundation foods is based on the highly consumed ingredients as reported in what we eat in America. We include market samples and agricultural samples where we have source metadata and data on acquisition date and the site of acquisition. We will consider new sources of samples and data through partnerships as FDC evolves over time. Our approach to analyses of foundation foods takes a number of factors into consideration, and that includes known sources of variability and the potential impact of the variability on composition profiles. We also look at historical reference numbers for components to be analyzed, and importantly, what data can be obtained in high quality for a relatively low cost, because all of this will be analytical. The components to be analyzed should be components of interest to scientists, healthcare providers, policymakers, and consumers. Some of the challenges we face are related to a balance between data quality, the cost, and the timeliness of obtaining these results. The next new data type in FDC is experimental foods. This data type includes foods produced, acquired, or studied under unique conditions, such as alternative management systems, experimental genotypes, or novel research or analytical protocols. These data do not generally fit well into any of the other data types, but are complementary to foundation foods. Experimental foods will provide links to agricultural systems, food science and processing, research and analytical approaches, and hopefully be of use and interest to data scientists who employ artificial intelligence and machine learning techniques. These data are extracted from peer-reviewed publications of research conducted by USDA scientists or supported by USDA. As foundation and experimental foods grow, we expect to enhance the link between the two, to continue to expand and adapt our approaches to collecting information to include in foundation and experimental foods, and expand relationships between food production and environmental impact to ensure a sustainable food system. So what's next for Food Data Central? First, a review of our accomplishments since the release in 2019. We've established incoming pipelines for analytical data and for data from industry. We've established an interface for USDA research data, and we've established collaboration and linkages with external databases. And so where are we going? We expect to expand data and metadata, enhance connections to diverse data systems, including other food composition data systems, facilitate the use of FDC as a resource for agriculture, diet, environmental, and health research, and finally, foster collaboration amongst public and private entities. And as examples, we would include the Periodic Table of Food Initiative by the Rockefeller Foundation, the existing Global Branded Foods Products Database, which was released in 2016 as a result of a public-private partnership, and develop a coalition of food systems interests to enhance data innovation at USDA. This does mean that we are setting ourselves up for shifting from looking at one number for a component in a single food to consider what is on the entire plate, because people eat food and not nutrients. There's never really a right or wrong answer, as long as you have enough food and enough variety on your plate. So our hope is that this information will help us to shift away from a fear of food, but begin embracing food because of the diversity in the components that they contain that together promote wellness. Our goal is to look ahead while honoring the past. So we do emphasize that the food on your plate may not be the food that was analyzed. Moreover, we want to emphasize the importance of dietary patterns, where food composition data and understanding of interactions amongst foods to assure that needs are met is an important consideration. We also aim for flexibility in the platform to permit new data types and new links to different data sets, and the application of data science approaches and connections to historical data. We hope to facilitate new applications, new collaborators, and new ideas. And we also know that we must show gratitude to the trailblazers and the generations to come. The past, Drs. Atwater, Watt, Holden, and all the federal staff and collaborators that made Standard Reference 1980 to 2019 possible. The present, who are our valued collaborators both within USDA and HHS, and the many partners in national and international research institutions, as well as the public sector. And the future, we hope to have our present collaborators and partners, but also to be named individuals and groups that share the goal of excellence in food composition from food production to human health. Thank you for your time and attention, and we look forward to your feedback. On this slide, I've listed the email addresses of the BHNRC team that work on Food Data Central, and we look forward to hearing from you.